Allison, what's going on?
Hello.
Hello. Okay, good. My microphone's working.
I'm sorry if someone walks in. I'm currently at work and I'm in my boss's office because he's in court right now. So I don't know when he's coming back.
All right. Well, that's a thing. I don't need details on that. That's cool.
He's an attorney. So
Oh, so he chose this. That's much better.
he
Okay.
chose it. He's not like in trouble. He's an attorney.
Oh,
So
that's much
he
better.
is in Will County.
You got to start with that. Come on.
Sorry.
We look very professional right now. You look very official. Like whatever you say, I should be writing down. That's what I'm getting the impression of.
You know, it's the law office vibes.
All right. What can I help with?
Riemann Sums.
Riemann sums. Okay. Let's just do a simple parabola, right?
Okay.
So let's make this 2x squared. That's the function. I really think that we should always be starting these problems by trying to gather insight until that just becomes so standard and so comfortable that we can jump ahead. But in all honesty, when I do these problems, I still do some side work that goes back to the story so that I don't mess up. So let's imagine that we want to make some rectangles here. Do you want the rectangles to touch on the left or right?
Right.
Sure, why not? Right. I mean, it makes absolutely no difference. So that'll be the first one. Let's pretend that touched. Yeah, this one touched. This one's going to touch. Okay, good. How far are we going to follow this curve? What's our domain? What do you want to play with?
Let's do 5.
Up 0 to 5?
Yeah.
Okay, great. How many rectangles?
1, 2, 3, 4. Let's do 5.
You want to do 5 rectangles? All right. So that one's going to be super easy. Let's just make it a little harder. Let's make it.
Let's do 10.
Divide
them in half.
4. Let's make it to 4. That way it's going to split up not so even, not so nice of numbers, right? Okay. We're going to force us to kind of play with the equations a little bit. All right. So if that's the case, let's go back through the whole thing. Let's start with rectangle 1. Rectangle 1 is going to have a width and it's going to have a length. What's the width?
The width would be, hold on. I'm not sure because
you got it. Look at the picture. Pull it from the picture.
Okay, so what I did was, because we got 5 parts that go to 4, I divided by 5 by 4 and got 1.25.
Good. So let's check. So you're saying that this right here is at 1.25.
Yes.
Good. What's the next one at?
2.5.
Good. What's the next one at?
3.75.
All right. What's the next one at?
Oh, it's at 5.
Tell me when we recognize a problem.
I should have done 4 divided by 5.
Good. Now, before you just kind of choose that as the other option, why would that make sense?
Because when you're adding up all the pieces, I should have gotten to 4, but I went over 4. I went to 5, which is how many chunks. So I had flipped the numbers.
Yeah, but that just tells me that what you chose doesn't work. That doesn't tell me that the other option makes sense.
Oh, because if I do 0.8 plus 0.8 plus 0.8 until I get there, I'll get to 4 instead.
That's just n justifies the means.
Oh.
Think about it like this. We had a length of 4, right?
Mm-hmm.
I wanted to separate that into what?
5 pieces.
Good. So I wanted to literally divide 4 into 5 pieces. It's a story.
So this is like where we do like the rectangle where I could put one on the inside, one on the outside. Okay.
Yes. So like now that you have that story, it's like, oh, I have a length of 4 that I want to break into 5 pieces. That means I have a 4 I want to divide into 5. Got it. Now, next time we hit it from the story makes logical sense. We don't have to guess and check anymore. You see how that evolution happens? Like, it's okay to say, we'll try something. I love trying something. It's the same way that I introduced the method of exhaustion approaches. Like, let's just try something. Let's understand that if that's wrong or if it's right, we don't stop. We interpret.
Okay.
Cool.
Got it.
All right, cool. So now that we have that, we're again going, okay, rectangle 1 is width times length. The width we said is going to be what now?
0.8.
0.8, which I'm going to write explicitly and would recommend you do the same for your notes as that.
Okay.
Right? The exact numbers are not nearly as important as the story. Calculators can always get us numbers. Story only comes from us. What about the length? I need to go up to the curve, right?
Mm-hmm.
And the curve was at 2x squared. So if now I erase these numbers and instead I am at 0.8, what is the height above 0.8? How would I find that?
So you would plug in 0.8 to the x.
Yep.
Because that's your x coordinate. So it'd be 0.8 times, hold on. Oh. I need my calculator.
Don't worry about the how. I don't need the numbers. I just want the method.
Oh, so you just plug in 0.8 and then square it because that's the equation.
And then multiply that by 2 because I've got a 2 in the equation, right?
Yeah.
So this is my height again. This is my width. That would get me a number. Great. Now I could do it for the second one. The second one is going to be same width, different width.
Same width.
Same width. So I've got a 4/5 all the time. What's the next thing I'm going to plug in?
You're going to plug in the height into the equation.
Good. What would that be in this case?
So it'd be 2 times 0.8 plus 0.8.
Good. So pause right there. Again, I don't need the numbers. I need the method. You did 2.8s, right?
Yes.
2 of these rectangle widths. And then you would plug that in.
Yes.
And then for the next one, we can now start to interpret. What would the third one be? Same width,
And
plug
then,
in 3 rectangle widths across to get my sideways. Plugging it into the equation gets me my vertical, right?
Mhm.
So if I now said, okay, let's go to rectangle 15. Rectangle 15 has the exact same width. It
And
has
then
15 of these 0.8s plugged in and squared, right?
Yeah.
Now there's not 15 rectangles here, so that doesn't make any sense. But like we've got the pattern. So
Mhm.
now what we'll do is if we want to really make this general, first of all, we would just do this 5 times and then we would get our estimate. But if we want to really go beyond that, we want to get like that expression that we would use, then we take this back to its pattern. We don't want to play with 5 rectangles anymore. We want to play with n rectangles. So every time we see 5, we want to split 5. We want to take that out. We want to replace it with n. Right? So instead of 4 divided into 5 pieces, it's 4 divided by n pieces for n rectangles. Instead of 2, well, I still got a 2. 2 times 0.8. 0.8 was the 4/5, right?
Mhm.
So it's now it's not 0.8 anymore. It's
4
4/nths. Exactly right. Plugged in squared. But every single time I went from 1.8 to 2.8 to 3. So it's not like I need to make it I of these rectangles because I increased every single time. So that gets me an expression for any rectangle now based on n splittings up.
Sorry, I'm just writing this down.
That's okay.
Okay.
So now we say, okay, what am I doing with all these rectangles? Once I got them, I'm adding them. I'm adding them starting at which one? I'm starting at the 0th one, right? How come? Because the first time I had, no, how many did I start with? I guess I started with the first. I went over 1 rectangle width. So I guess I'm starting with the first rectangle. So not I equals 0, I equals 1. I went over 1 rectangle width. How many did I go up to? N, because I didn't specify in this case. What is it that I'm doing addition with? I'm doing 4 over n times 2 times I times 4 over n squared. That's my setup. Adding up all the rectangles. So it's just that now I'm adding up how many rectangles? An arbitrary n, a variable number of rectangles. Okay, but do you see how it's literally the same addition as saying, like, look what I did right here. I would have had 4/5 appear everywhere. Good. 4/nths appears everywhere. Got it. I would have had 2 appear everywhere. Good. 2 appears everywhere. I would have steadily ramped up the number of rectangle widths. Good. That's my ramping up, my I. And then I would have always had a rectangle width that's appearing in the inside. Good. I've got a rectangle width appearing on the inside that I would have plugged in and squared. Like it's the same pattern. I'm just grabbing it from its method. I'm not grabbing it from its number.
Got it.
right? So
And
now
then
from here, this is a great way where we can start to say like, okay, let's start to do some what looks like magic math when we're talking summations. Would it make sense over here that if I added up all these rectangles, every single one has a 4/5?
yes.
Would it make sense that I could factor 4/5 out of that addition?
Yes.
Yeah, because everything has a 4/5 times it, right? So does it make sense in this addition that I can factor out a 4 over n?
Mm-hmm.
Right, because that would be in every single one of them. Can I factor out a 2?
Yes, because it's
I
in
could
all of them.
absolutely factor out a 2. Would I be able to expand this and simplify this?
Yes.
Because I would have squared and done whatever to these numbers, right?
Yeah.
So, and if I did that, then I would have had this thing that keeps changing squared, but this thing would have just been 4/5 squared every single time. So every single time I have a 4/5 squared, that means I can pull out front a 4/n squared. Like I can pull these things out because I would have normally pulled things out. This isn't anything different than the factoring we've playing with. It's just that now we're not choosing to write it with so much ink. And then we're left with I equals 1 to n of, well, I squared. That's the only thing I can't factor out because it changes every time.
And then from there, you could do the summation. So
Yeah.
then it would be because it's squared, would it be the 3 or like the n parentheses and then all that divided by 3?
Yes.
And then you would multiply it by
And
the
then you'd
half.
simplify, we'd run it to a limit, et cetera, et cetera.
Because I guess like I'm still not like comfortable with like the sigma stuff yet, but I understand how to do what we were doing before, where it's just like
Yeah.
R1, R2, R3. Is it okay if we just do that?
Yes. So for if you didn't have to yes. Let's just go back to yes. Yes.
Okay.
If you just did the if you just had the addition as addition written across the paper as addition, total